All right, find a comfortable position and let your body feel heavy and relaxed. Let the day's thoughts drift away like clouds passing in the sky. Tonight, we are going on the grandest journey imaginable, a slow and peaceful trip to a place so far away that the light from it has been traveling for millions of years just to reach us. We are going to visit our nearest major galactic neighbor, the great Andromeda Galaxy. To start our journey, let's imagine we are standing outside on a perfectly clear, moonless night, far away from the lights of any city. We look up at the familiar constellations, and our eyes drift towards a part of the sky named after an ancient Greek princess, Andromeda. And if we let our eyes adjust to the deep darkness, and if we know just where to look, we might see it. It doesn't look like much. It's not a bright, twinkling star, but a faint, fuzzy, elongated smudge of light, like a tiny, ghostly fingerprint on the black velvet of space. Most people, if they noticed it at all, would probably think it was just a faint cloud. But what you are looking at is the most distant object the human eye can see without any help. That faint little patch of light is a galaxy, a swirling city of stars, much larger than our own Milky Way. And the light that is entering your eye at that very moment began its journey long, long ago. The Andromeda Galaxy is about 2.5 million light-years away from us. It's a number so large, it's almost meaningless. So let's just sit with what it implies. A light-year is the distance light travels in 1 year. So the light from that fuzzy smudge has been traveling through the void for 2.5 million years. When that light left Andromeda, our own species, Homo sapiens, did not yet exist. The great ice ages were still in the future. It's an ancient, ancient light, a postcard from a time long before human history. And what is it a postcard of? It's a picture of a truly colossal structure. That faint smudge is a galaxy that is home to approximately 1 trillion stars. That's a 1 with 12 zeros after it. For comparison, our own Milky Way galaxy is thought to have somewhere between 100 and 400 billion stars. So Andromeda is significantly larger and more populous than our home galaxy. It is the big brother in our little cluster of galaxies. In terms of sheer size, from one edge of its sprawling spiral arms to the other, the Andromeda Galaxy is over 220,000 light-years across. It's a vast spinning island of stars, gas, and dust. So, let's begin our journey. Let's leave our vantage point on Earth and slip the gentle bonds of our planet's gravity. We rise above the blue and white marble of our world, past our moon, past the other planets in our solar system, past the Kuiper belt, and even past the ghostly theoretical Oort cloud. We are now in interstellar space, the space between stars, but still within our own Milky Way. But our destination is much farther than that. We must push on, leaving our entire home galaxy behind us. As we travel outwards, the beautiful, swirling disk of the Milky Way, with all its billions of stars, would shrink behind us until it too becomes a faint, majestic smudge of light in our rearview mirror. We are now entering the true deep, the vastness of intergalactic space. The journey is quiet and profound. The space between galaxies is one of the most perfect vacuums in nature, colder and emptier than anything we can create on Earth. For millions of years,
This is our view, the receding light of our home galaxy behind us and the growing, still distant light of our destination ahead. It's a journey defined not by speed, but by immense, quiet patience.
This vast, dark space between our two galaxies isn't entirely empty, but it's close. We are part of a small cluster of galaxies called the Local Group. It's a small cosmic village of about 80 galaxies, most of them tiny dwarf galaxies. The two dominant members, the two great titans of the Local Group, are the Milky Way and Andromeda. They are like the two largest cities in the county, gravitationally pulling all the smaller satellite galaxies into their orbits. After our long journey, lasting for what feels like an eternity, we begin to approach our destination. The faint smudge of light that we saw from Earth has now grown into a spectacular, breathtaking sight. It fills our entire view, a colossal spinning disk of light tilted at an angle to us, giving us a magnificent panoramic perspective. We have arrived at the outskirts of the Andromeda Galaxy. We don't just plunge into the main disk. A galaxy like Andromeda is much larger than what we see in pretty pictures. It is surrounded by a vast, spherical, and almost invisible structure called a stellar halo. This is the galaxy's ancient attic. It's a ghostly sphere of stars that extends for hundreds of thousands, perhaps even 1,000,000 light-years in every direction from the main galactic disk. The stars here are very old, some of the first stars to form in the galaxy's history. They are red, cool, and metal-poor, meaning they are made of almost pure hydrogen and helium from the early universe. They are spread incredibly far apart, like lonely flickering embers from a long extinguished fire. Drifting through this halo, we would feel a deep sense of ancient history. We are in a realm of cosmic ghosts, the first generation of Andromeda's children. Also scattered throughout this vast halo are dense, beautiful clusters of stars, known as globular clusters. These are like ancient, miniature galaxies in their own right. A single globular cluster can contain hundreds of thousands or even millions of very old stars, all tightly bound together by gravity into a dense, glittering ball. Andromeda has several hundred of these orbiting it, like a swarm of bees around a giant flower. Each one is a self-contained city of ancient suns. Now, we drift down from the sparse halo and towards the main event, the bright, flat, spinning disk of the galaxy itself. As we get closer, we can see its magnificent structure. It is a classic spiral galaxy. From here, we can see the great sweeping arms of stars and gas, curving outwards from a bright, glowing center. The space between the arms is not empty, but is much more sparsely populated with stars. The arms themselves are where all the action is. These are the active, bustling neighborhoods of the galaxy. Let's gently guide our imaginary ship into one of these majestic spiral arms. The view inside is completely different from the quiet emptiness of intergalactic space. We are surrounded by light and color. The spiral arms are the galaxy's stellar nurseries. They are filled with vast, swirling clouds of interstellar gas and dust called nebulae. These are the regions where new stars are being born.
Some of these nebulae are lit up from within by the hot, young stars they have just created, and they glow with a beautiful, characteristic pinkish-red light. This is the light of excited hydrogen gas, the raw material of creation. It's a truly beautiful and serene sight, a cosmic cloud painted with the light of newborn stars.
The stars that are responsible for lighting up these nebulae are the very ones that define the spiral arms. The beautiful bluish-white tint of the arms comes from the presence of incredibly hot, bright, and massive young stars. These are the O and B-type stars, the same kind of stellar rock stars that back in our galaxy can end their lives as black holes. They are dozens of times more massive and thousands of times more luminous than our Sun. But they live very short and very fast lives, burning through their fuel in just a few million years. The spiral arms are essentially traffic jams of star formation. They are density waves, slow-moving ripples of compression that sweep through the galactic disk. As a cloud of gas and dust enters a spiral arm, it gets squeezed. This compression is enough to trigger the collapse of the cloud, giving birth to a new generation of stars. And because these brilliant blue stars are so short-lived, they don't have time to travel very far from where they were born. They live and die right there in the spiral arm, which is why the arms shine so brightly with their intense blue light. Our own Sun is currently drifting through a smaller spur of one of the Milky Way's spiral arms. Weaving through these bright regions of starbirth are dark, intricate ribbons of cosmic dust. These are the dust lanes. They are not holes in the galaxy, but thick clouds of tiny particles, mostly carbon and silicon, which obscure the light from the stars behind them. They give the spiral arms their beautiful, detailed and textured appearance, like a painter's brushstrokes on a glowing canvas. They are the shadows that give the light its definition. As we drift through NGC 1731, we see a dynamic and constantly changing landscape of light, gas, and shadow. Now let's turn our ship away from the bright, bustling spiral arms and begin a new journey, inwards, towards the heart of the galaxy. As we travel, the scenery changes once again. We leave the regions of active star formation behind us. The brilliant blue stars become rarer, and the glowing red nebulae fade away. We are entering the galactic bulge. The bulge is the dense spheroidal hub at the center of the spiral. It's a much older, much more settled part of the galaxy. The stars here are no longer confined to a flat, rotating disk. Instead, they move on much more random, inclined orbits, like a swarm of bees buzzing around a central hive. And the stars themselves are different. They are mostly older, cooler stars, shining with a soft, yellowish or reddish light. These are stars more like our own Sun in its later phases, or red giants, stars that have been around for billions and billions of years. The density of stars in the bulge is incredible. Here on Earth, in our quiet suburban spiral arm, the nearest star to our Sun is over 4 light-years away. But in the galactic bulge, stars are crowded much, much closer together. The night sky from a hypothetical planet in Andromeda's bulge would be a breathtaking, almost overwhelming sight. The sky would be filled with thousands of bright stars, some shining as brightly as Venus or Jupiter does in our own sky.
there would be no true darkness, just a soft, golden, starlit glow from dusk until dawn. It's a very different kind of environment, a dense, ancient city of stars. Many spiral galaxies, including our own Milky Way, are now thought to have a bar-shaped structure at their very heart, a dense, elongated bar of stars from which the spiral arms unwind.
And now we approach our final destination on this tour, the very heart of the Andromeda Galaxy, its nucleus. This is a place of extreme physics and deep mystery. For a long time, astronomers thought the center of Andromeda was a single bright point of light. But as our telescopes got better, particularly the Hubble Space Telescope, they discovered something very strange. Andromeda's core is not a single point, it has a double nucleus. When we look at the very center, we see two distinct concentrations of stars, which astronomers have creatively named P1 and P2. They are separated by only a few light years. What could cause a galaxy to have two nuclei? The leading theory is that one of them, the fainter one, is the remnant of a smaller galaxy that Andromeda swallowed a long time ago. Its core has not yet fully settled into the center of Andromeda, and it is still orbiting the true central nucleus. It's evidence of galactic cannibalism, a quiet clue to Andromeda's violent past. And at the very center of all this, at the true gravitational heart of the galaxy, lies the same type of object that sits at the center of our own Milky Way, a supermassive black hole. But Andromeda's is much more of a monster than ours. While the black hole at the center of the Milky Way, Sagittarius A*, weighs about 4 million times the mass of our Sun, the supermassive black hole at the heart of Andromeda is estimated to be over 100 million solar masses. It's a true behemoth, a gravitational titan holding 1 trillion stars in its sway. Despite its enormous mass, Andromeda's black hole is currently very quiet. There isn't a huge bright accretion disk around it, which means it's not actively feeding on large amounts of gas and dust right now. It is a sleeping giant at the heart of a vast, spinning city of stars.
And so our tour of Andromeda is complete. We've seen its ancient halo, its vibrant spiral arms, its old central bulge, and its mysterious double-hearted core. Now for the final leg of our journey, let's do something impossible. Let's imagine we are standing on a quiet, rocky planet, orbiting a calm, yellow star in one of Andromeda's outer spiral arms. We wait for night to fall. As the sky darkens, a truly spectacular sight comes into view. Hanging in the night sky is a beautiful, bright, spiral-shaped galaxy. It's tilted perfectly, showing off its graceful, swirling arms, its glowing central bulge, and the dark dust lanes that trace its structure. It is the most magnificent object in the sky, and it is our home. We are looking at the Milky Way. From this incredible vantage point, 2.5 million light-years away, we can see our own galaxy, not as the familiar faint band of stars we see from Earth, but as the external, majestic structure that it truly is. We could point to a faint, unremarkable spot in one of its outer arms and say, "There, that's where the Sun is. That's where Earth is." It's a view that gives a profound sense of perspective. It shows us that our galaxy, which seems so vast to us, is just one of countless islands in the great cosmic ocean. It's a quiet reminder of the scale of everything, of the beauty and complexity that exists far beyond our own world. And with that final, humbling view, our journey comes to a peaceful end. It's time to drift back across the great void, back to our own familiar corner of the universe, carrying with us a little piece of that cosmic perspective.
So let's begin that deep dive, starting right back at home on that clear, dark night. When you look up at that faint, fuzzy patch of light in the constellation Andromeda, you are participating in an act of observation that goes back over 1,000 years. The first known written record of the Andromeda Galaxy comes from the Persian astronomer Abd al-Rahman al-Sufi, who described it in his Book of Fixed Stars way back in the year 964. He called it a small cloud, which is a perfect description of how it appears to the naked eye. For centuries after, that's all it was to the people who noticed it, a curious, cloudy spot in the heavens. When early European astronomers began to map the sky with telescopes, they catalogued it too. Simon Marius is credited with the first telescopic observation in 1612, and in 1764, the famous French comet hunter Charles Messier added it to his renowned catalogue of fuzzy things that are not comets. He labelled it M31 or M31, a designation astronomers still use today. But even to them, it was just a nebula, a cloud of gas presumed to be relatively close by, floating amongst the stars of our own Milky Way. The true, mind-boggling nature of that little smudge remained a complete mystery. Let's linger on that for a moment. That light is 2.5 million years old. When we talk about a light year, it's a measure of distance, not time. It's the distance that a beam of light, the fastest thing in the universe, can travel in one full year. Light travels at about 300,000 kilometers per second. So in 1 year, it covers about 9.5 trillion kilometers. And the light from Andromeda has traveled that distance 2.5 million times over. It's a number that our brains are simply not equipped to handle. But it gives us a profound sense of connection to the past. We are seeing Andromeda as it was when early hominids were first walking the plains of Africa. It's a form of natural, cosmic time travel.
And what a picture that time travel reveals. Our imaginary spaceship, now poised to leave, has a view of two galactic titans, the Milky Way behind us, Andromeda in front. It's worth pausing to appreciate the tale of the tape between these two cosmic heavyweights. For a long time, based on its visible light, astronomers thought Andromeda was much, much more massive than the Milky Way, perhaps 2 or 3 times as much. Its glowing disk of stars is certainly more spread out, spanning over 220,000 light-years from edge to edge, while the Milky Way's main disk is closer to 100,000 light-years across. And as we said, it's home to about 1 trillion stars, a population that dwarfs our own galaxy's 100 to 400 billion. However, more recent and detailed studies, especially those measuring the mysterious and invisible dark matter that surrounds both galaxies, have complicated the picture. Some studies now suggest that the Milky Way might actually have more dark matter than Andromeda, making our home galaxy the more massive of the two overall, even if its starry disk is smaller. It's a quiet,
ongoing debate among astronomers, a reminder that even our closest galactic neighbor holds deep mysteries. For our journey, let's just appreciate them as two magnificent, roughly equal giants, the two gravitational anchors of our local cosmic neighborhood. This neighborhood is called the local group. It's not just the Milky Way and Andromeda floating alone in the void. They are the dominant members of a small cluster of galaxies, a little gravitationally bound village of about 80 known members. Most of these are tiny dwarf galaxies, faint wisps of stars that are gravitationally tethered to one of the two big spirals. Our Milky Way has its own famous satellite galaxies, the large and small Magellanic Clouds, visible from the southern hemisphere. Andromeda, likewise, has its own collection of smaller companions, like the ones we can see in telescopes designated M32 and M110, huddled close to the main galaxy.
The third largest member of the local group is the Triangulum Galaxy, another pretty spiral about half the size of the Milky Way. The rest are all much smaller dwarf galaxies with names like Leo 1, the Sculptor Dwarf, and Andromeda 2. The local group itself is a gravitationally bound system, all its members orbiting a common center of mass, which lies somewhere in the vast empty space between the Milky Way and Andromeda. It's our little cosmic family, our island of galaxies in the much larger universe. So, let's begin our journey in earnest. Our imaginary ship leaves the last vestiges of the Milky Way's outer halo behind. We are now officially in intergalactic space. The quiet here is more profound than any silence you can imagine. The emptiness is more complete than any vacuum we can create on Earth. Here, in the void between galaxies, the density of matter drops to just a few stray atoms per cubic meter. It is as close to perfect nothingness as you can get. The temperature is equally extreme. It's not the bone-chilling cold of deep space in the movies. It is the absolute fundamental cold of the universe itself. The background temperature here is just 2.7 Kelvin, or about minus 270 degrees Celsius. This isn't just random cold, it's the faint, residual afterglow of the Big Bang itself, a bath of ancient microwave radiation called the cosmic microwave background that permeates all of space. We are floating in the oldest light in the universe. To try and grasp the scale of the 2.5 million light-year journey ahead of us, analogies fall apart, but let's try. If you're in a commercial jetliner traveling at a steady 900 kilometers per hour, it would take you about 3 trillion years to reach Andromeda. It's a distance that makes our own solar system, which seems so vast, shrink to an insignificant speck. It's a journey defined not by speed, but by an almost eternal patience.
As we travel, our view changes in slow motion over what would be millions of years. The magnificent swirling disk of our home galaxy, the Milky Way, shrinks behind us. At first, we can still see its structure, the bright central bar, the graceful spiral arms, the familiar nebulae. But as we push on, those details fade. The arms merge into a soft, blended glow. The galaxy becomes a flattened, luminous disk. Then, it's just a bright, lens-shaped smudge. Finally, after an immense amount of time, our home becomes just another point of light among the few other distant galaxies visible in the sky.
all of human history, every person who has ever lived, every war, every piece of art, all contained in a single, fading star-like object. It's a truly humbling perspective. In front of us, our destination slowly grows. For most of the journey, Andromeda 2 is just a slightly brighter, fuzzier star. But as we get closer, entering the final few 100,000 light-years of our trip, it begins to resolve itself. It starts to take shape, transforming from a smudge into a magnificent tilted disk that fills our entire field of view. The faint glow becomes the light of 1 trillion individual suns. Awe is the only appropriate feeling. We have crossed the great void. We have arrived at the outskirts of the Andromeda Galaxy. We don't just plunge headfirst into the bright, busy spiral arms. A galaxy like Andromeda is like a great city, and we are arriving in its vast, sparsely populated suburbs. We are now drifting through the galaxy's stellar halo. As we mentioned, this is a huge, roughly spherical region of space that surrounds the entire visible galaxy. It's the galaxy's ancient attic, and it's much, much bigger than the bright disk itself. If the main disk is 220,000 light-years across, the halo might extend for 1,000,000 light-years or more in every direction, its edges mingling with the halo of our own Milky Way.
The halo is a ghostly, ethereal place. The stars here are incredibly spread out. You might have to travel for dozens, even hundreds of light-years to get from one to the next. They are also the galaxy's oldest residents, true first-generation stars that formed over 10 to 12 billion years ago. They are what astronomers call metal poor. In astronomy, metal is a slightly funny term for any element that isn't hydrogen or helium. Since these heavier elements are forged inside stars and spread through supernova explosions, the very first stars had almost none of them. They were made of the pure primordial gas from the early universe. Finding these ancient metal-poor stars in the halo is like a form of cosmic archaeology, telling us about the conditions when Andromeda was first being born. The story of the halo itself is one of violence and galactic cannibalism. It wasn't born this way. It was built up over billions of years as Andromeda's powerful gravity captured and shredded smaller dwarf galaxies that wandered too close. The stars of those consumed galaxies were pulled out into long, looping streams of stars that eventually dispersed and mixed together to form this vast, ghostly cloud. The halo is a graveyard, the blended remnants of countless small galaxies that Andromeda has eaten over its long lifetime. As we drift through this serene but haunted region, we would encounter some of the most beautiful objects in the galaxy, the globular clusters. These are magnificent, ancient cities of stars. Imagine a perfectly spherical snow globe, but instead of snowflakes, it's packed with hundreds of thousands of old golden-hued stars, all orbiting each other in a tight gravitational dance. A single globular cluster is a breathtaking sight, a dense, glittering ball of ancient suns. Andromeda has a rich system of these clusters, with nearly 500 of them known, more than our own Milky Way possesses. Each one is a relic from the early universe, a fossil of the galaxy's formation. Their origins are still a bit of a mystery. Some may be the dense, surviving cores of those small galaxies that were otherwise torn apart and absorbed into the halo.
Drifting past one would be awe-inspiring. The density of stars at its center is so great that the night sky there would be ablaze with brilliant light from dusk till dawn. Now we leave the ancient ghostly halo behind us and drift down towards the main event, the place where most of the stars live and most of the action happens. We are descending towards the great, flat, spinning disk of the galaxy. From our vantage point, high above, we can see its magnificent structure clearly. It's what astronomers classify as a type SB spiral galaxy, meaning its arms are moderately kitely wound around a large, bright central bulge. As we get closer, we can see the incredible detail. The beautiful, sweeping arms are traced with the brilliant blue light of young stars. Between the arms are darker gaps, regions with older stars and less gas and dust. The whole thing is spinning, though not like a solid pinwheel. The stars in the outer parts of the disk orbit much more slowly than the stars closer in. Our own Sun takes about 230 million years to complete one orbit of the Milky Way. A star at a similar position in Andromeda would have a similar galactic year. It's a slow, graceful, majestic rotation on an unimaginable scale. Let's now gently guide our imaginary ship into the heart of one of these grand spiral arms, to see what a galactic neighborhood really looks like up close.
The experience of entering a spiral arm is a gradual immersion in light and color. From a distance, the arm looks like a solid, glowing structure, but up close, it reveals itself to be made of countless individual points of light, all moving in a slow, collective dance. The space between the stars is still vast, but it's no longer the near-perfect emptiness of the intergalactic void or the sparse halo. Here we are surrounded by a thin, ethereal medium of gas and dust, the raw material for future stars and planets. The spiral arms themselves are best thought of not as fixed structures, but as persistent patterns, like a slow-moving traffic jam on a cosmic highway. The stars and gas clouds are the cars, and the spiral arm is the traffic jam itself. As clouds of gas drift into the arm, they are compressed by the higher density. They slow down and they bunch up. This compression is the critical trigger for star formation. The cars in this analogy, the individual stars and clouds, will eventually pass through the traffic jam and continue on their orbit into the sparser region between the arms. But the traffic jam itself, the spiral arm pattern, remains. It's a self-perpetuating wave of creation, sweeping slowly through the entire galaxy. And the evidence of that creation is all around us. The most beautiful sights within the arms are the nebulae, vast, dreamlike clouds of gas and dust. We can see the famous emission nebulae, often called HI regions. These are the true stellar nurseries. They are lit up from within by the intense ultraviolet radiation of incredibly hot newborn stars. This radiation energizes the surrounding hydrogen gas, causing it to glow with a beautiful, characteristic pinkish-red light, much like the electricity flowing through a neon sign causes it to glow. They are like soft, rosy clouds, cosmic wombs where thousands of stars are coming to life.
We would also see another type of nebula here, the reflection nebula. These are clouds of interstellar dust that are not hot enough to glow on their own. Instead, they shine with a gentle, second-hand light, reflecting the light of nearby young stars. Because the tiny dust particles are better at scattering blue light than red light, for the same reason our own sky is blue, these nebulae have a beautiful, ethereal bluish tint. They are like cosmic ghosts, hazy veils of light surrounding the brighter stars. And weaving through all this glowing gas and reflected light are the dark nebulae. These are not holes in space, but incredibly dense, cold clouds of dust and molecular gas that are so thick they completely block the light from any stars located behind them. They appear as dark, intricate ribbons and patches against the bright backdrop of the spiral arm. These dark clouds are the very earliest stage of star formation. Deep within their cold, dark hearts, gravity is slowly pulling matter together into dense knots that will, millions of years from now, ignite as new stars. They are the seeds of future light, currently hidden in shadow. The brilliant blue-white light that gives the spiral arms their distinct color comes from the stars that are born within these nebulae. These are the O and B-type stars, true stellar giants. They are dozens of times more massive and can be hundreds of thousands of times more luminous than our own quiet sun. They are the universe's rock stars, burning through their nuclear fuel at a furious rate. And because they are so massive, they live very short and very dramatic lives, lasting only a few million years. This is a cosmic blink of an eye. This is why we only find them in the spiral arms, where they were recently born. They simply don't live long enough to drift out of the arm and into the regions between.
The life cycle of these giant stars is what enriches the galaxy. During their short lives, their intense stellar winds, powerful streams of particles flowing from their surfaces, push on the surrounding gas clouds, creating beautiful bubbles and sculpted shapes in the nebulae. And when they die, they do so in the most spectacular way imaginable: a supernova explosion. In its final moments, a single one of these stars can briefly outshine the entire galaxy. This explosion blasts all the heavy elements that were forged in the star's core, the carbon, the oxygen, the iron, out into the surrounding space. This material, this stardust, then enriches the nearby clouds of gas and dust. The shock wave from the supernova can also be the trigger that compresses these enriched clouds, starting a whole new wave of star formation. This next generation of stars will then incorporate those heavy elements into their own systems, eventually forming rocky planets and perhaps providing the raw materials for life. The spiral arms are a dynamic, beautiful engine of cosmic recycling, a place of constant birth, death, and rebirth. Now, let's slowly guide our ship away from the vibrant, youthful energy of the spiral arms. We begin a new journey, a long, slow drift inwards towards the very heart of the Andromeda Galaxy. As we travel, the scenery begins to change again, slowly and subtly. The brilliant blue stars become rarer and are replaced by a much older population. The glowing red nebulae of starbirth fade away. We are leaving the bustling, creative suburbs and heading for the ancient, crowded downtown. We are entering the great central bulge of the galaxy.
The galactic bulge is a huge, tightly packed, roughly spherical swarm of stars that sits at the center of the spiral disk. It's a much older and much more settled part of the galaxy. The reason the stars here are different is because star formation in this region happened much more rapidly and much earlier in the galaxy's history. Most of the gas and dust in the bulge was used up billions of years ago. The massive, hot blue stars that once lived here have long since expired. What's left is a population of much older, longer-lived stars. They're mostly stars like our own Sun, or stars that have aged even further into yellow giants and red giants, giving the central bulge a soft, warm, yellowish-golden glow. The orbits of the stars here are also very different. In the spiral arms, most stars move in relatively flat, orderly, circular orbits around the galactic center. But in the bulge, the stars move on much more random, eccentric, and inclined orbits. They swoop in and out from the center at high speeds, plunging up and down through the central plane. It's less like cars on a highway and more like a swarm of bees buzzing around a central hive. The density of stars in the bulge is truly incredible. Here on Earth, in our quiet suburban neighborhood of the Milky Way, the nearest star to our Sun, Proxima Centauri, is over 4 light-years away. It's a vast, lonely distance. But if you were on a hypothetical planet orbiting a star deep within Andromeda's central bulge, the nearest star might be only a few light weeks or light months away.
The night sky from such a world would be a breathtaking, almost overwhelming sight. It would be permanently ablaze with thousands of brilliant stars, dozens or even hundreds of them shining as brightly as the brightest stars and planets do in our own sky. There would be no true darkness, just a constant, soft, golden, starlit glow, washing out the faint light from any distant galaxies. It would be a beautiful, but perhaps very different environment for life to evolve in. Many spiral galaxies, including our own Milky Way, are now thought to have a specific structure at their very heart called a galactic bar. This isn't a place that serves drinks. It's a vast, elongated, bar-shaped structure composed of billions of stars stretching across the central region. This bar acts like a cosmic funnel. Its gravitational influence is thought to channel gas and dust from the inner parts of the spiral arms inwards towards the very nucleus of the galaxy. This process can feed gas to the central supermassive black hole and can sometimes trigger bursts of star formation right near the galactic center. Andromeda is not thought to have a very prominent bar, appearing more as a classic spiral, but the dense bulge serves a similar role as a gravitational hub. And now, we approach our final destination on this grand tour, the most extreme and mysterious place in the entire galaxy. We are heading for the very heart of Andromeda's central bulge, its nucleus. This is a place of incredible density, extreme physics, and deep, ancient secrets. For a long time, astronomers observing the core of Andromeda saw it as a single, intensely bright point of light. But as our telescopes, particularly the Hubble Space Telescope, got powerful enough to peer through the glare, they discovered something very strange and unexpected. Andromeda's core is not a single point. It appears to have a double nucleus. When we look at the very center with incredible resolution, we see 2 distinct concentrations of light, 2 bright knots of stars, which astronomers have designated P1
and P2. They are separated by a distance of only about 5 light-years. For a galactic core, that's incredibly close. What could possibly cause a giant galaxy like Andromeda to have 2 distinct nuclei? It seems to defy logic. The leading theory, and it's a fascinating one, is that this is compelling evidence of galactic cannibalism on a grand scale. The brighter of the 2 knots, P2, is thought to be the true, original center of the Andromeda Galaxy. The other, fainter knot, P1, is believed to be the dense, surviving core of a smaller galaxy that Andromeda swallowed, perhaps billions of years ago. According to this idea, the smaller galaxy was torn apart by Andromeda's immense tidal forces, its stars assimilated into the bulge and halo, but its dense central core managed to survive the disruption. This captured core has not yet had time to fully settle into the center of Andromeda. Instead, it is currently in a looping, eccentric orbit around the true galactic center. It's like a final ghostly remnant of a long-dead galaxy still dancing around its conqueror's heart. It's a quiet, subtle clue that tells us galaxies are not static islands. They are dynamic, growing, and often violent systems that are built up over eons by consuming their smaller neighbors. And at the very center of all of this, at the true gravitational heart of the galaxy, the point around which everything else ultimately orbits, lies the same type of object that sits at the center of our own Milky Way, a supermassive black hole.
As we've learned, these objects are a standard feature of large galaxies. But Andromeda's central black hole is a true monster, far larger and more massive than our own. The supermassive black hole at the center of the Milky Way, known as Sagittarius A star, is a respectable heavyweight, weighing in at about 4.3 million times the mass of our Sun. It's an incredible object. But the supermassive black hole at the heart of Andromeda dwarfs it. Current estimates place its mass somewhere between 100 and 200 million times the mass of our Sun. It is a true gravitational titan, a silent, invisible ruler holding 1 trillion stars in its sway. We can't see the black hole itself, of course, but astronomers can weigh it by observing the stars that are orbiting it very closely. Using the incredible resolution of the Hubble Space Telescope, they can track the motion of individual stars in the nucleus as they whip around the unseen center. By measuring the speed of these stars and the size of their orbits, they can use the simple laws of gravity to calculate the mass of the central object they are orbiting. The incredible speeds of these stars, thousands of kilometers per second, reveal the presence of an immense, compact mass that can only be a supermassive black hole. Despite its enormous mass, Andromeda's black hole is currently very quiet. There isn't a huge, bright accretion disk of superheated gas swirling into it like we see in more active galaxies known as quasars. This means it's not actively feeding on large amounts of gas and dust right now. Like our own galaxy's black hole, it is mostly dormant, a sleeping giant at the heart of a vast, spinning city of stars. It quietly governs the orbits of the stars in the central bulge, patiently waiting for its next meal.
And so our long and detailed tour of the Andromeda Galaxy is complete. We've looked back in time from our home on Earth, journeyed through the cold, quiet, intergalactic void, and arrived to explore this magnificent island universe. We've drifted through the ghostly, ancient stars of its halo, witnessed the vibrant birth of new suns in its beautiful spiral arms, traveled through the dense golden swarm of its central bulge, and peered into the deep mystery of its double-hearted core. Now, for the final leg of our journey, let's do something impossible. Something that requires only the quiet power of our imagination. Let's imagine we are standing on a quiet, rocky planet, orbiting a calm, yellow star in one of Andromeda's outer spiral arms. We've found a safe harbor. We wait for the local sun to set and night falls. As the sky darkens, a truly spectacular and deeply unfamiliar sight comes into view. Hanging in the night sky is a beautiful, bright, spiral-shaped galaxy. It's tilted perfectly, showing off its graceful, swirling arms, its glowing central bar, and the dark dust lanes that trace its magnificent structure. It is, by far, the most glorious object in the sky. And it is our home. We are looking at the Milky Way. From this incredible vantage point, 2.5 million light-years away, we can finally see our own galaxy not as the familiar, faint, milky band of stars we see from Earth, but as the external, majestic island universe that it truly is. We could try to point to a faint, unremarkable spot in one of its outer arms and say, "There, that's where our sun is. That's where Earth is."
It's a view that gives a profound and almost overwhelming sense of perspective. It shows us that our galaxy, our home, which seems so impossibly vast to us, is just one of countless beautiful islands floating in the great cosmic ocean. It's a quiet reminder of the true scale of everything, of the beauty and complexity that exists far beyond our own world. And with that final, humbling view, our journey comes to a peaceful and gentle end. It's time to drift back across the great dark void, back to our own familiar corner of the universe, back to our own solar system, to our own pale blue dot. We can carry with us a little piece of that cosmic perspective, a quiet sense of our place in this vast and wonderful tapestry. The Andromeda Galaxy is more than just a faint smudge of light. It's a history book, a stellar nursery, a gravitational dance, and a mirror to our own home. It's a quiet reminder that the universe is not static, but is constantly in motion, a place of birth, life, and slow, majestic change. And as you settle deeper into comfort, let the scale of it all be a soothing thought. Let the quiet turning of the galaxies be a gentle rhythm to carry you into a deep and peaceful rest. The problems of a single day on a tiny planet can feel very small indeed when you've just taken a quiet trip to another galaxy. Sweet dreams.